notes, so we're continuing in the notes 2.4. So this is the part where we're going to talk about piecewise functions. Kind of in the middle, we talk about linear models, then we're talking about piecewise functions, linear piecewise functions. And then we'll look at a special type of linear model called direct variation, and that's the last part of this chapter. Section, not chapter, section. Alright, so first, piecewise defined functions. So piecewise defined functions are functions which, again, it's literal. They're defined differently on different parts of their domain. Alright, so on their domain, one piece of it's defined by one type of function, a second piece is defined by a different function, and maybe a third piece is defined by a third function. Right? It's all part of the same function, but different parts are defined by different functions. So the graph is part of it, is all of the parts are graphed using different functions. And so it's just easier to kind of look at an example. So the first example here is the function f of x, so it's a function, where x minus 1 is the piece that we use if my x values are between 2 and negative 4, including negative 4 but not including 2. And then I use the function negative 2x if my x values are between positive 2 and positive 4, including both those endpoints. And so the first question that we ask is, what's the actual domain of the function? It's got two piece domains, but what's the actual domain of my total function, right? Total domain. Well, the lowest value the x value can be is negative 4. And then I look here, 2 does exist, that exists on my other function, so that exists at 2. And then my highest value my x can be is 4. And so the domain is all values from negative 4 to positive 4. So when I graph it, the picture should be graphed between positive 4 and negative 4. Right, then I ask you to evaluate it, so find some function values at some values that I've picked. And so f of negative 3, so what it is here is that's the x value, right? X is negative 3. Well, what function do I use if x is negative 3? Well, I use the first function, right? Because that's negative 3 lands between 2 and negative 4, so I use the x minus 1, plug it in for x, so negative 3 minus 1 comes out negative 4. Alright, then 2, now I have to be careful with 2, because 2 is in both parts, but in the first piece, 2 is not a part of it because it's not equal to. But 2 is a part of the second function because there is equal to there, so I use the second one. Negative 2 times 2 is going to come out negative 4 as well. Alright, then f of 4, so f of 4 is in the second piece, right? 4 exists, there's equal to, and so negative 2 times 4 comes out negative 8 for that answer. And then the last one's sort of a trick question, f of 5. Remember, our original domain only exists between 4 and negative 4, so 5 is outside the domain. So this is not in the domain. If it's not in the domain, we say undefined, right? It's not defined in the domain. It does not exist at 5. Right? The function only exists between 4 and negative 4. All right, next thing we're doing is we're going to graph the function. So I'm going to write it here so I have it to look at. So I've got x minus 1 if I'm between negative 4 and 2. And I'm negative 2x if I'm between 2 and 4. And then I'll answer the continuity question. Alright, so graph it first. So what you do is you sort of take it piece by piece. So I'm going to take the first piece. So this is the first piece. And I look at it. Remember, this is the y equals the function part. So it's y equals x minus 1. If I'm between negative 4 and 2, I include negative 4, but I don't include 2. And since they're lines, right, these are all linear cases, I know it's going to be a straight piece of a line, so it's going to be a segment of a line. It's going to start at negative 4 and stop at 2, and so that's what I use to graph it. And so I know I want to start at x equals negative 4. Well, when x equals negative 4, I plug that in, y equals negative 5. And so that's the point negative 4, negative 5. Negative 4 is included, right? That's what the equal to means. And so when I graph that, it's going to be a closed point. All right, then this is going to stop at 2. Stop at x equals 2. Well, when x equals 2, again, I'm plugging it in this function. I'm just looking here at 1. And so I'm going to plug 2 in here for x. I'm going to get 2 minus 1, which is 1. So it's going to stop at the point 2, 1. But this time, 2 is not included, right? Not equal to. And so that point was where it stops. But it doesn't exist there. Well, we use an open point to indicate that. Meaning, It's where the piece of my line stops, but doesn't exist at that endpoint. But everything up to it exists, right? 1.9 exists, 1.99 exists. It just doesn't exist at 2, but 2 is where I'm going to stop. And so we indicate that by drawing an open point. Alright, so there's the first piece of information, and then I'm going to do the same thing for the second piece, and then I'm going to graph. Alright, so this is the second piece. It's piece 2. And so it's the y equals negative 2x between 2 and 4, including both 2 and 4. So again, I'm going to draw this line between 2 and 4, including 2, so both endpoints this time are going to be closed. So the piece starts at x equals 2. So when x equals 2, y equals negative 4, and so the point 2, negative 4 is where we start, and it's closed. It's going to stop at x equals 4 when x equals 4, y equals negative 8. So 4, negative 8 is where it stops, and that is also closed because it exists at both ends. Alright, that's the information that I'm going to use to graph the picture. So again, I'm going to draw my lines. There's my x-axis and my y-axis. Alright, so the first piece, I'm going to draw the point negative 4, negative 5 as a closed point, and the point 2, 1 as an open point. Alright, so negative 4, negative 5. So 1, 2, 3, 4, 1, 2, 3, 4, 5, negative 4, negative 5, closed. Alright, then the second piece is at 2, 1, and it's open. So 2, 1. But it's an open point. Oops, open point at 2, 1. Does through there, connect my dots. And there's the first piece. Alright, so there's piece 1 graphed between negative 4 and 2. Now I do the same thing for the second piece. So the second piece starts at 2, negative 4. So 2, negative 1, 2, 3, 4. So 2, negative 4, closed. Alright, 2, negative 4. And then 4, negative 8. So I actually need to draw this a little bit more down. Alright, so that was negative 5, 6, 7, negative 8. So 4, negative 8. And that was also closed. Okay, 4, negative 8, and then connect the dots. Alright, let's try to draw a straight line, semi-straight there. And so there is the graph of that function, right? And it does only exist between 4 and negative 4, right? Stops at 4 and negative 4. And then the last question that was asked was, is the function continuous on its domain? So its domain is between 4 and negative 4. So is it continuous between 4 and negative 4? And the answer is no. It's not continuous. At x equals 2, there's a break or jump in the function. And so continuity is if a function can be drawn without lifting your pen up or pencil up. And that's not the case here because there's a break between the first piece. I can draw it, but then I have to lift my pen up to draw the second piece. And so there's discontinuity. And so there's ever discontinuity if there's a hole in the function, an asymptote in the function, or a break in the function. This one has a break at 2. 2 is the only place where it's not continuous. It's continuous everywhere but 2. But 2 is where there's a break, and so it has discontinuity. Alright, so now we're just going to practice graphing some functions. So I'm just going to look at sort of graphs and then talk about continuity with them as well. I'm going to do a couple more of these graphically. Just so you know, there is a way to graph them on the calculator. It's actually fairly complex to do it. I think it's easier to graph these by hand. But I did post a video online in case you're curious about somebody does walk through how to graph piecewise functions on the calculator, and feel free to watch that if you want to graph them on the calculator. But like I said, I'm not going to because I actually think it's easier, especially with these linear cases, to graph them by hand. So my second example, suppose f of x equals the function 3 if I'm between negative 4 and 0, x plus 3 if I'm greater than or equal to 0. Alright, so there's two pieces. First piece of the function is a constant function, f of x equals the constant 3, if my x values land between negative 4 and 0, not including 0. Then I'm a part of the line, x plus 3, but only if my x values are 0 or positive, right? So this one's going to go off to infinity, 0 or more. So again, I'm going to graph it and talk about continuity. So graphing it first. So I'm I'm going to do the same thing I did before. I'm going to take my first piece. My first piece is the constant function, the horizontal line. Y equals 3 over negative 4 to 0, including negative 4, but not including 0. So that kind of look like a bracket there. I'll draw that more parentheses-wise. Parentheses. I need to make my bracket stronger. There. Alright, so includes negative 4, doesn't include. So again, it'll start at x equals negative 4. Y is always 3, so the point negative 4, 3, and that's closed because it exists there. The horizontal line will stop at x equals 0, y is 3. So the point 0, 3 is where it stopped, but that's an open point. All right, then the second piece is the line y equals x plus 3 from 0 to infinity, right? Because x is going to be bigger than 0, so I can pick any positive value for x. So it starts at 0 because it exists there, and then anything after that. So we don't really have a stopping point. We do have a starting point. That's important. I'm going to start at x equals 0. When x equals 0, y equals 3. So I start at 0, 3, and that's going to be closed. And then I don't have an ending point, but in order to graph a line, I need at least another point. So I just need another point. And you can pick any point as long as you pick a value where it exists between 0 and infinity. Pick anything one. I'll pick x equals 2. Well, if x equals 2, y equals 5, and so 2, 5 is my second point. And it's closed as well. The line goes through it. It's going to go off for forever because it's infinite. Alright, there's my information that I'm going to use to graph it. So now to graph it. Alright, so there's my y-axis, there's my x-axis. So the first piece is the horizontal line, negative 4, 3. 1, 2, 3, 4. So negative 4, 1, 2, 3. Closed. Negative 4, 3 is where that function starts. Stops at 0, 3, and it's open. So 0, right, is at the axis. 0, 3, but that's an open point. It's a flat line, right? Y equals 3. Starts at 4, 3, stops at 0, 3, and doesn't exist at 0, 3. Alright, so there's the first piece. Now the second piece, and this is where we're going to again talk about continuity. The second piece starts where the other one ended up, right? This is stopped at 0, 3. This one started at 0, 3. And so what happens when I go graph it? I get to go, when I start my next function, it starts here, and I actually get to fill this dot back in because this function starts there, and it exists, and it's closed. And so it starts at the point 0, 3, so I close that 0, 3 in. And then I draw my second point, which is at 2, 5. So 2, 5. Which it doesn't stop at 2, 5. Remember, this goes off for forever. Right? Shooting to infinity. And so it's just going to go through that point, and then I'm going to keep drawing it, and it goes off for forever. And so there's my second piece. And so in this case, it is continuous on its domain, which is from negative 4 to infinity, right? Starts at negative 4. I can draw it without lifting my pen, if I can trace it without lifting my pen. So I start at negative 4. Since this existed here and it closed it in, it exists there, and I can continue to draw it for forever without lifting my pen. And so over its domain, negative 4 to infinity, it is continuous. There's no breaks, gaps, or asymptotes. All right, let's do one more example with 3. All right, so f of x is equal to the function 1.5 minus 0.5x if x is between negative 3 and negative 1. Include negative 3, don't include negative 1. It's negative 2x if I'm between negative 1 and 2, including both negative 1 and 2. And then it's the constant 5 if I'm between 2 and 5. Oops, that can't be equal to, sorry. Between 2 and 5, not including 2 in this case, and including 5 in that case. Alright, so there's 3 parts to this one. So I'm going to have 3 pieces when I go to graph it. So piece 1 is the line y equal 1.5 minus a half x over negative 3 to negative 1. Include negative 3, but don't include negative 1. So I'm going to start at x equals -3, plug it into that equation, so I'm going to get half 3 is going to give me half, so it's 3. So point -3, 3, and that's closed, right, because it's included. That line stops at -1. So when I plug -1 in, I'm going to get +2 out. So -1, 2, and that time it's open, right, because I don't include my -1. Alright, so there's my first piece. Now my second piece, which is y equal -2x, between -1 and 2, including both ends. So this one's got a very short piece. It starts at x equals -1, y equals +2, so -1, 2. And if you'll notice, that's where this one stops. So we are going to connect like we did before, as that's closed. And then this one stops at +2. When it's +2, it's -4, so 2, -4, and it's also closed. So both of these ends are closed. Then I have my third point. Let's see if I can fit it in here. Third piece is the line y equals x. So it's a horizontal line between 2 and 5. Alright, starts at x equals 2, y has to be 5, so it's the point 2, 5, but this is open, because it doesn't exist at 2. And then we'll stop, that's where it starts, stop at x equals 5, y equals 5, so the point 5, 5 is where it stops, and that's closed. Alright, so starts and stops at those points, so there's all my information, and then I just go ahead and I graph it. Alright, so the first piece. There's my y-axis, and there's my x-axis. Alright, so the first piece is between -3, 3, so -3, 1, 2, 3, +3, closed. So -3, 3, stops at -1, 2, so -1, +2, but that was an open point. -1, 2, open point. Connect the dots. So it's just a very small segment. But where that one stops at -1, 2, the next one actually starts. So I'm actually going to fill that point in, right? This one starts. The next is I'm done with piece 1. Now I'm on to piece 2. When I start this second piece, it actually starts at that closed point. So I'm going to close it in because it starts there. So it closes in at -2, 1. So I just close that in. And then goes to 2, -4. So 1, 2, 1, 2, 3, 4. So 2, -4, closed as well. And I connect the dots, and it does go through the origin. And so the first two pieces are continuous, right? Because one stopped and the other started right where it stopped. All right, the last piece is the horizontal line y equals 5 between 2 and 5. So I start at 2, 5, and that's open, closed at 5, 5. So 1, 2, 3, 4, 5. So 2, 5, open, 5, 5, closed. And so it's that piece. And so its domain goes from -3 to 5, and it does exist everywhere between -3 and 5, and it's not continuous at x equals 2, right at 2, there's a break. Alright, so it's not continuous there. And there's the graph of that function. Like I said, there is a way to graph it on the graphing calculator. I actually think these are easier to do by hand because they're pretty straightforward by hand. But if you want to look at it, I've included the video there in the YouTube, them walking you through how to do it by hand, and it's up to you if you want to do it or not. Alright, so we stop there with piecewise functions.